Hello everyone, my name is Pedram Mahzari. I'm a reservoir engineer and research associate at University College London Earth Sciences. Today I'm presenting a review of our study on CARBFIX project where fully coupled hydrothermal, mechanical and chemical modeling was performed for CO2 storage and mineralization at Husmeli region of Helishady reservoir in Iceland. CARBFIX project is a very smart and exciting implementation of CO2 disposal where evidence from field data, laboratory observation, and numerical simulation demonstrate favorable and relatively fast CO2 mineralization in basaltic formations. Here is the list of people contributing significantly within our team at UCL and our collaborators at CARBFIX company and Reykjavik Energy. We are grateful and also acknowledge this collaboration under the EU-funded project called Science for Clean Energy. Firstly, I will give a brief introduction about geothermal reservoirs and Helishady Reservoir where the CARBFIX project is ongoing. Then our methodology and results of characterizing the fluid flow path. In a fractured reservoir, we will discuss, since we have used a stress-dependent permeability discussion, and the role and impact of stress-dependent modeling will be given. After that, a summary of induced seismicity for the reservoir will be discussed, as one of the advantages of coupling geomechanics is ability to identify stress distribution within the reservoir. Subsequently, the results of the coupling geochemistry and CO2 and H2S mineralization during CARBFIX project are presented. As an introduction, geothermal reservoirs are known to be the green alternative for fossil fuels. It's usually considered as a water-saturated reservoir with high temperatures. On the right-hand side, the deep geothermal wells drilled in Cornwall is illustrated, where injection and production wells are drilled in fractured granite formation. From reservoir engineering point of view, geothermal reservoirs are associated with reinjection or recycling of the produced geothermal fluid. Reinjection of cold water can cause thermal effects between fluid and the host rock. Also, any system under injection or withdrawal can lead to induced seismicity or tremor. For instance, Cornwall geothermal project in well testing period has recorded more than 50 tremors with maximum magnitude of 2.2. Also, in terms of long-term energy extraction, the thermal and chemical effects of reinjection can bring about precipitation and dissolution processes in wells and within the reservoir. I should point out that geothermal reservoirs are not the zero-emission systems. Production of geothermal fluids are usually associated with CO2 and H2S production. H2S is a hazardous gas and cannot be released into air. In Iceland, CARBFIX began by the idea of reinjection of H2S, which was then upgraded to a CO2 fixation as well. In this slide, I give an overview of CARBFIX project. In conventional CO2 storage scenarios, aquifers and oil and gas reservoirs are considered for their structural trapping to keep the CO2 underground. There has been numerous studies for the caprock integrity and the concerns over that and storage capacity. However, in the CARBFIX, the predominant mechanism of trapping is mineralization of CO2 and H2S into carbonates and pyrites. The process, as explained here in reaction terms, you can see on the right-hand side, is about dissolution of basalt, which releases divalent ions that can react with bicarbonates further into the reservoir to form carbonate minerals. Therefore, the risk of leakage is minimal, and also storage capacity is abundant as mineralization can take place within the reservoir on the pore surface rather than the pore volume. In southwest of Iceland, where Helishady geothermal power plant is located, the temperature of basaltic formation can reach to 300 degrees Celsius. Here is the map of the temperature map of the reservoir, and here is where reservoir is located in the Iceland. Also, the energy extraction is associated with the release of 36,000 and 9,000 tons of CO2 and H2S annually. Besides, a reinjection activity in Husmali area cause induced seismicity. But the key to understand the different processes, such as CO2 storage and induced seismicity, which are planned. CO2 storage is planned to in CARBFIX project, is to characterize the fluid flow path in the fracture network. Tracer tests are widely used for fluid flow path characterization in geothermal reservoir. A batch tracer test was performed in 2013 at Husmali area using well HN17, highlighted with blue arrow, and it is injected in depth of 800 meter and 1600 meter, as is highlighted in this figure. Here is the results of the tracer test. As you can see that from these two profiles, the majority of the tracer was recovered in these wells. From the other tracer recoveries, as highlighted by red, and the black one, which are these profiles, it is clear that the major fluid flow is southwest to northeast, which is consistent with the fault orientation. Therefore, the faults and fractures are the main controlling media for the fluid flow, and they are vertically extended structures. Therefore, we need to characterize these vertically extended structures. To characterize these vertically extended faults and fractures, a campaign of drone imaging were performed, and here is the fractures and dikes extracted from the high-resolution images. Then the images were analyzed, which is indicated predominant dikes observed southwest to northeast direction, and the faults are the fractures orientation are the northwest to southeast. This implies that the faults are the main flow paths and the fractures can establish connection between the faults. To construct the model, we have considered three sources of data. Geological interpretation of the tracer test, where the faults are identified as the main flow paths. You can see they have been identified a direct communication between the wells through the faults. Drone surface imaging that are used for constructing the fracture networks. In addition, we have used the absolute permeability and effective stress relationship as measured in laboratory, where we used 4 different core plugs, one with the intersecting fractures, one with 3 microfractures, one in 1 microfractures, and one without any fractures intact sample. And we identified that the 3, and this is basically the novelty of the work. It is not very common to use a stress-dependent permeability for history matching of the tracer test. And from our analysis, we understood that for our Iceland case, the 3 microfractures is the representative case for our system. The model was primarily discretized along the faults. The faults are these black lines highlighted in this map. It is refined in the middle, where the active wells are drilled. The model is extended with large grid blocks away the sector. You see here the areal permeability distribution. Also, the model has 7 layers, which is based on the major feed zones. The major feed zones are similar to perforations oil industry. The model, as you can see, we have these blue circles. They represent the feed zones. The model is used to history match the tracer test. The tuning parameters for history matching are horizontal and vertical fracture probability and fracture porosity for each layer, for each individual layer, and also some fracture probability and porosity between the wells areally. Here is the results of history matching using CMOS auto history matching software. The tracer profile for all 4 neighboring wells were matched simultaneously. The resultant horizontal and vertical multipliers, we use multipliers to adjust permeability and porosity, indicates 2 different geological flow units. The reservoir has high permeability for the bottom layer, whereas it has high vertical permeability in the middle layer. The top layer has high fracture porosity. And low we can say low fracture porosity can be translated to low mixing between injected and resident fluid, which is important for chemistry of CO2 fixation. Here is the fracture porosity and permeability maps obtained from history matching. We have these dots are the feed zones, or we can say perforations. We have low fracture porosity between these 2 wells. This is one well, and this is another well, which is in line with the fast travel of tracer between these 2 wells. Also, we have high communication. Here we have a permeability multiplier. We have high communication between these 2 faults. We have one fault here, and we have another fault here. And we, from history matching, we identified that we have high communication between these 2 faults. One of the advantage of old CMG results software was the ability to compute the streamlines, which can be really helpful to identify well-to-well communications. Here we show 2D and 3D streamline of the flow from injector towards the producers. A clear vertical streamline, you can see here is a clear vertical streamlines can be identified from the 3D streamline maps. Also, minimal streamlines can be seen in the southern part of the reservoir, whereas we have significant streamlines in the northern part of the reservoir, which is really important in identifying the effective stress distribution within the reservoir. Here we want to show the impact of stress-dependent permeability on the tracer test profiles. We have performed a forward simulation without the stress-dependent permeability to generate the tracer recovery profiles. Not only the amount of the recovery tracer is notably different. Here is the difference between the stress-dependent and without any geomechanics. Not only the amount of the tracer recovery is significantly different, the arrival time is also significantly different. Therefore, stress-dependent properties should be used in tracer test analysis for fractured reservoirs. Since the system is highly sensitive to stress-dependent modeling, we perform a separate history matching to characterize the flow path without geomechanics, which is the routine approach in the industry. Here you can see the comparison of the 2 calibrated models. Interestingly, the reservoir properties can be substantially different for 2 models. In other words, for fractured reservoir, it may not be a robust methodology to use a hydro-only model for tracer test analysis. One of the advantages of geomechanically coupled model is to study the seismicity and tremors due to injection activities. Controlling induced seismicity is a challenge for geothermal industry, and it makes headline for geoenergy operations, as can be seen in these snapshots, these news snapshots. Even in a publicly accepted country like Iceland, induced seismicity can make the residents angry. However, here is the recorded seismicity in Helishady power plant, which reached to a magnitude of 4 in 2011. From this plot, it can be seen that the injectivity has a strong relationship with the injection temperature, which indicates the temperature-dependent permeability around the injector. You can see that as the permeability drops, the injection rate goes up, and we have an inverse relationship between the temperature of the injection fluid and the injection rate of the injector. To see how our simulator can estimate the induced seismicity, here on the left-hand side, the location of the two major tremors recorded in host milli area is highlighted. It took place in the northern part of the injection area. Here is the injection area, and it took place here in the northern part. Also, we show here a map of the effective stress distribution in the top layer, superimposed on the field map. The red color shows the high stress accumulation, and the blue indicates the low stress parts. In terms of the location, our calibrated model could estimate that the northern part of the reservoir is likely to experience tremor, which is similar to the field observations. This can add more confidence on the calibrated model, as the location of the stress accumulation is directly controlled by the flow path. However, I should say that the more work is ongoing for this part, because induced seismicity and the characterization of the seismicity is a very complex process. Having characterized the flow path, the model is now ready for simulation of CARBFIX CO2 fixation. So we considered the stress-dependent calibrated model and activated the geochemistry in CMG. Three main minerals are used: basalt as the primary mineral or the host rock, carbonates and pyrrhus were the secondary minerals, forming due to geothermal activity. I should point out that we have ignored clay minerals due to numerical convergence issues. Although the model was calibrated using tracer tests performed at HN17, CARBFIX was carried out at HN16, which is highlighted with this purple arrow. However, it is conceivable that the HN16 and HN17 have similar flow path. You can see that they are closely placed. To test that, we can use the results of another tracer test performed at HN16. Along with the CO2 and H2S, a non-reactive tracer was continuously injected at HN16, and the tracer recovery was measured at the producing wells. Therefore, using the calibrated model, we can validate the model using an independent this tracer test as a forward simulation approach. Here is the results of the forward simulation for the tracer profiles as compared against the field data. You can see this is the simulation curve, and the dots are the field data. There is a good similarity between the field data and the simulation results, which can validate our methodology for characterizing the fluid path. I need to reiterate that this is a forward simulation. So we use the calibrated model and we run the simulation, and we just compare the results with the field one, this is an independent simulation. Now that we have tested our calibrated model, with an independent tracer test, we have defined two cases for geochemical interactions or geochemistry. One is the injection of the plain water. There is no CO2 or H2S involved. And one is with the CARBFIX, where we have tried to store and mineralize CO2 and H2S within the geothermal reservoir. First, the plain water injection was considered. Here we show the effluent concentration in the producers compared with the injector. This one, the flat line is the injector, and these lines are the producer. We have calcium, magnesium, and aluminum. It is clear that there is an increase in concentration of calcium, aluminum, and magnesium, albeit in a very small quantities. In terms of the dissolution and precipitation, this is a map of the dissolution and precipitation. I can say it's a change in pore volume. In terms of the dissolution and precipitation, this image shows the dissolution in the vicinity of the injection, in the vicinity of the injector due to cold water injection. On the other hand, we have minor precipitation in the vicinity of the producers. This one is a producer, this one is a producer, this one is a producer. We have a minor precipitation in the vicinity of the producer due to the pressure drop and the different conditions around the producers. What if we add CO2 and H2S to the injection stream? Here we want to show the impact of CO2 and H2S related ions on basalt dissolution. Here we illustrate the overall mineral changes in the sector with respect to time. The green one is the basalt dissolution. There is no CO2 H2S involved. This blue one is the basalt dissolution with the actually enhanced with the presence of the CO2 and H2S. Evidently, the blue line indicates significantly higher dissolution compared to the routine geothermal operation, which is the green line. Here we present the simulation results for tracer distribution in the third layer after 2 years of the CO2 and H2S injection. There's a clear contrast. We have non-reactive tracer distribution here, and we have bicarbonate, which is related to the injected CO2 distribution within the third layer. So there is a clear contrast in propagation of non-reactive tracer and CO2 related species, which indicates the notable retention of CO2 due to mineralization. CO2 and H2S can basically CO2 and H2S can hardly reach this well HE44 after 2 years. Here we show the 3D image of the change in pore volume due to CO2 precipitation and H2S precipitation. In terms of the minerals formed within the reservoir, the bottom part of the sector is mostly affected. Although overall the pore volume is not compromised, you can see the values are very small. The pore volume is not compromised due to precipitation. For the minerals, basalt dissolution happens in tandem with the carbonate and pyrite formation. This observation is in agreement with field report, where the efficiency of H2S fixation is higher than that of CO2. It is worth noting that the basalt dissolution deviates. Here you can see the basalt dissolution deviates from the linear trends after around 5 years of injection. In order to keep the dissolution level to the same level, can be suggested to increase the CO2 concentration in the injection stream to increase the acidity and keep the basalt dissolution going. In the past 2 years, the effluents at the producer were analyzed regularly. In this figure, we compare the bicarbonate concentration from simulation results against the field data. Overall, we can see a good match from the simulations given the uncertainty in geological model, reaction kinetics, and numerical approaches. If we go to the details, we expect the red on red and the black on black, which is not the case in this figure. However, in general, we can say, given the error of the measurements and other uncertainties, we can see we have a good match in the effluent of the produced fluid and the field data. In general, from our simulation, we identified that the injectivity was not compromised or even noticeably affected by CARBFIX activity. We have noticed that the permeability reduction of less than 1% after 5 years of the CO2 storage can happen due to CO2 mineralization. In conclusion, a fully coupled hydrothermal-mechanical and chemical simulation was performed using CMG GEM, and we also used CMOS to auto-history match the tracer test results. We have calibrated the fluid flow path using stress-dependent properties, and we used a calibrated model to identify the location of induced seismicity, and we understood that the properly calibrated model can be used to detect the induced seismicity. Also, adding the geochemistry to our model, we identified that CO2 and H2S mineralization could be modeled successfully for host melee reinjection sector, and also it can be we saw that it can be a sustainable process for at least the duration of the simulation, which was 5 years. Thank you very much. Thank you very much for your attention. This work was part of the Science for Clean Energy Consortium funded by EU Horizon 2020 Research and Innovation Program. You can see the logo of our collaborator here, and we thank CMG for allowing us using their software and publishing the results. Thank you very much.